Welcome you all to this Cryo-EM course. Previously we discussed about the anatomy of the electron microscope as well as the cryo-electron microscope. We discussed about the electron gun to accelerating stack, then different types of lens system. It is coming from condenser lens to intermediate lens, and then finally we discuss about the sample holder, how we image our sample, and then finally we are recording our data in direct electron detector or CCD camera or plate camera. So now when we are inserting our sample, our electron beam is passing through the sample, and then we are imaging or we are recording those data in either CCD camera or in direct electron detector. Now most of the time we are using direct electron detector. Last class also I discussed that based on our requirement we have to decide what kind of detector is required. For mostly for the negative staining imaging or room temperature temp, we do not need direct electron detector because beam induced drift or motion will be not there. But for the cryo-electron microscope, it is really mandatory to have the direct electron detector, and then we record the data using the direct electron detector. Now the first question it is coming, how we are getting our data or images? Is it how it is forming the image? So when we have a sample, you all know that, so sample will stay near the goniometer, and then electron beam will go through that, and then there will be a multiple other lens system which will magnify our data, and then you will get an image. So now let's see how we can get. So from now on we are I am going to take another 4 to 5 classes where we will discuss about how we are getting an image. So what is the principle behind that image? We are not going to discuss too much about the mathematical details about the how we are getting the diffraction and then how it is forming the images. So I will just try to explain it in a very basic way. Mostly we will use the ray diagram, but some basic knowledge we should have how image formation it is happening. So let us discuss about that image formation, how we are getting the image formation. So today's class will be image formation. So okay, so I will just use the notepad and mostly okay. So let me just show you one thing, that next 2-3 classes whatever I am going to focus mostly things are taken from this optics book from the Hicks. So if anyone is interested and if you want a details knowledge about the diffraction pattern, different type of diffraction or Fourier transform, someone can go through that. But for mostly for the biologist we do not need so much details about that diffraction pattern, or I can say that newcomer or who is the new users, we do not need so much details. So if someone is interested, or if someone is interested about the advanced material, then definitely you can go through this book. Otherwise it is not required at this moment for the new users. This is mainly required for the expert users, but definitely we have to go through some basic material, how wave is forming, what is wave, how they are interacting, and if they interact what kind of resultant wave we are expecting. Because whenever we will talk about the diffraction pattern and then we are getting our images, there will be one term it will come, it is called the contrast transfer function, and then we have to know that what is the basic of that contrast transfer function. So that we are going to discuss about all of this, but in a very basic form, not in a too much mathematical details. So if we consider that we have a wave, so anything that we already discussed, right, that different types of wave, it is starting from the different kind of frequency, that radio frequency or the microwave or infrared light, or if we just say visible light. And then again we are talking about the ultraviolet light, as well as X-ray, electron and gamma ray. We are whenever talking about those, they are following a certain path. Okay, so they are coming as a wave form. It is not like a straight line all the time. So it will go like a certain kind of wavy form. So waveforms means that when you are talking, so if we don't talk, it is a silent, no vibration, nothing is there. So then whenever we are talking, there will be a some kind of disturbance in the air. So same thing for the light also, or any kind of rays, when they are traveling, they are following certain pathway. So they are not a straight line all the time. So they will be up and down like this. So that is basically called the wave. And whenever I use a ray diagram, I used a straight line all the time, but definitely it will not follow a straight line, it will be a wavy line always. So if you just remember that when we are discussing about our normal any diagram, that okay, we have a object here and we are using a straight line, right, we are using a straight line, then we are making a crossover point here and it will go all the way down, and then it is giving us an image here. But basically what we have to do, it should be a wavy nature will be there. Okay, it should come like that. Then someone can ask that, then why are you using the straight line? Because straight line, sometimes it is very difficult to use that wavy line to do a ray diagram. So that is one of the major reason we mostly use a straight line to do any kind of ray diagram, and that is we are going to do that. But same time we have to understand when there is a wave, so how they are, when they converge in one particular point, what it is happening, and when there is a, they are not converging, they are just normalizing each other, how they are normalizing each other. So that is the reason it is better to know the little bit details about this wave, how this light or the X-ray or electron is traveling. So let's take a look. So whenever we will talk about a wave, couple of parameters are very important, and that we have to know. So if we have this one, you can see this is the x, this is x axis and this is y axis. And when we are talking about a wave is traveling, wave can travel any direction. So it can go through the y or x or in between x and y. So any wave, if we are considering that we are starting a wave like this, it is going like that. So what property do we have in this particular diagram? If we just consider that this wave has a amplitude, this is called amplitude. Okay, so that height we are considering. So if you just consider that you are so you are looking in front, you are standing in front of a sea, and then that waves are coming, right. So that sometimes those waves height is very high. So that height, if we consider, that is called the amplitude. Now the next one is coming the angle, what angle it is moving. So that is called the phase. So amplitude is one, then next one it is coming phase, and I already told that which direction they are going is a positive or negative, or through the x and x axis or y axis or in between that. So now any wave, so if you just consider this is a complete wave, it is starting from here, is going all the way down and then going down and going up again. So here near this x axis everything is 0. Then it has some value. If you just consider, if this is a +1, and you can consider that this value it is coming -1. So, here if you just consider this is the amplitude plus amplitude and this is the minus amplitude. So, you can see this is a up and down form. So, here I just pointed only one wave, this is called the 1 lambda or wavelength, okay. And this height is called the amplitude and the angle is called the our phase. Those are the couple of points are very important that we have to remember. And then if we are not changing the amplitude, the wave propagates in one particular direction. It may be minus or it may start from 0 and going towards the positive, or it can start from negative going towards the positive, or maybe from positive to negative. So, this is the direction we have to consider, and whenever the wave will propagate, this angle is going to change. So, phase is going to change. So, if there is a multiple waves are together, here we are only talking about one particular wave. So, when there is a multiple waves are coming together, we have to consider how they are interacting with each other. Based on that, we are talking about the constructive interference or destructive interference. So, constructive interference means when they come together and if they are matching with the phase, their amplitude will increase, and that is we are going to discuss more in the later stage. Let us take a look in a details about if I have to draw a normal wave, how I can draw that any wave. So, I have a straight line, I am using a different color for the wave pattern. So, I am starting from here, it is going all the way to 0, then it is going again all the way to 0 and then negative, and then again all the way to 0 and so on, and it will keep going on. Now, what I was talking, this is the 0. So, it has no wavelength change. So, I told you that if you just consider this particular wave, this the complete one full cycle when it is going, we can tell that it is completing one wavelength. So, in a particular in a certain distance, in a unit distance, how many waves are going. So, how many oscillations are there, that is called the frequency. If I just consider 1 second time and 1 second time wave is just oscillating 1, that means the frequency is 1. And now, if we just consider that wave is oscillating 100 times, so up and down, very fast it is going like that. So, that is how many oscillations are there, that is called the frequency. So, we know that frequency is we will denote by f, and we will say that lambda, this is equals to lambda is wavelength. Okay. So, now here also phase we discuss about that is the angle. Now, let us mark this wave in a different position and see if we can find out the angle as well as the wavelength change. So, if we are considering this one, this is my full wavelength, right. So, I can tell that this is complete one wavelength, right. Now, this is the amplitude, I will consider this is minus a and this is plus a, is my amplitude. Now, starting from 0, I am just marking this one that okay, this is it is just travel 1/4 of the wave. If this is my complete wave starting from here to here, then if I just consider this particular point, it is just 1/4 of that wave length, right. It is 1/4 of that wavelength. So, now I can tell that this is lambda by 4. Now the angle, if we just consider that what is the angle here, we can tell this is pi by 2, so 90 degree. So now if we just consider this particular point here, it is half lambda, lambda by 2, and travel total one complete half circle. So you can start from here and it is going to the half circle. So we will put everything in the phasor diagram and show you how we can calculate this angle also. That will be very helpful. Right now you just see these things, how I am correlating those points. Now the next one is coming that okay, this is lambda by 2. Then what about this particular point? In this particular point we can see we have a negative amplitude. So if you just consider it is a 3 lambda by 4, okay, and so angle wise this will be 3 pi by 2. Now when we have a full cycle, this is 2 pi, and it will keep going on like that. If we just consider the other one, that particular this one, we can say that it is a 5 lambda by 4 and angle will be 5 pi by 2. Now what about this negative side? If we just consider this particular side, we will get it like that. Okay, so we started from 0, so it is exactly opposite of this one, right? If I just consider this particular point and this particular point, it is just opposite in negative. So amplitude is same, it will always amplitude, only the direction is changing. So it will be minus pi by 2 and length will be minus lambda by 4. Now if we just consider this particular point, so this particular point is just the opposite direction of this one, right? So now we can write it that this particular point, it will be lambda by 2 and it will be minus pi. So from this diagram you know that okay, so we can correlate this angle with our wavelength, the what wavelength, which angle, if it is a moving in a one direction, and also from the sign we can consider that it will be a negative or the positive. Now next go to the next one. Okay, so far we discuss about that. Okay, when we have to draw a wave, we have to know the angle, which angle it is going. So most of the time any wave function, if we want to write it, so we need a particular formula for that wave function. So we can say it that any wave, that f of x, you can write it that amplitude, then sine, it will be omega t plus any angle. So t is time and omega is the angular. So here that is omega will be 2 pi by t or 2 pi by f. Or if you just consider that okay, you want to represent this wave in a different form, that okay, how much distance it is traveling and time also, you can represent it like that. Okay, we have that x comma t, and so if we just consider, we will just use this when t equals to 0, we can write it like that, a sine kx, where k is the spatial frequency, okay, and x is the distance. Now here in this particular case you can see that we do not have any phase difference, so there is no phase angle difference here. So we can modify these things in, you can consider that wave has a velocity v and it is going through a positive direction in x, then we can change that formula in something like that. Okay, y, if we just consider x and t, so in this case we can write it that a sine k x minus v t. So, I am trying to bring that time function also here, that x distance and the time both are playing an important role. So, those formulas at this moment are not very important, but those are very basic formulas that we are talking about, that okay, if we want to write any wave, we can write it either sine curve or a cosine curve, based on that how this wave starting, from which direction it is going, based on that it will be either sine or cosine form, and then we have that this omega into t plus as well as the phase change between that wave. So, let us take a look based on the time how the changes are happening in this wave. So, if we come, so here the spatial frequency is k, we can say that spatial frequency, I mentioned that spatial frequency here k. K basically we can say that it will be 1 by lambda. So, this is called the spatial frequency. Spatial frequency. Okay. So, let us take a look that when there is a wave and it is going x and y direction, and in a phasor diagram we want to plot it, and the angle also we want to calculate from that one. So, that will be easier for us to plot each and all the waves together. So, here I will start with this one, and then I will go back to my slide which will help us to explain. So, I will just change the color. So, this is our first wave, right, that we started discussing, that this is our first wave. It is starting from 0, this is by lambda by 4, this is half lambda, and this is full lambda, and this one we already told that 3 lambda by 4, right, and here t equals to 0, and this is the velocity in this direction. Now, in a phasor diagram I want to plot this one. How I want to plot it? So, it will be we are going to plot the angle, and here this is the amplitude, right. So, if we have a diagram like a circle, and starting from this particular point we will draw a vector here. This length is basically equivalent to the amplitude of this wave, okay, and we are starting at 0 position. This is my y axis, this is my x axis. Now, I will use a different color. So, at the 0 your wave, it will stay like this. So, there is no change in the angle, right. Now, we are doing it the second one. If we consider that is the reason we put it v here, because we have some velocity. Initially we are measuring this one when t is 0. Now, t time we are considering that it will divided by 8. So, there is some kind of change, and that we are going to plot it, okay. So, this one, the wave propagates in this direction. We will just keep this one. So, it moves all the way here, it will come here. So, now if you try to see that, okay, the maximum amplitude, if we just consider this is plus a and this is minus a, this minus the plus amplitude, the highest amplitude is shifted now here. So, you can see it is shifted somewhere here, and also this negative amplitude, whatever is the maximum, it is also shifted towards in this direction. So, there is a motion because of this time, wave is moving in this particular direction with a velocity v, and there is some changes. So, now if we want to plot this one we can tell that okay, this is 0, this is now lambda by 4, and this is you are getting lambda by 2 and then lambda by 3 and so on. So now I want to plot this one. If we just consider that, what is the major change here? The major change is that the amplitude, total amplitude, there is no change, right? So amplitude is same for this one and this one. There is, I didn't change the amplitude. Only change is happen in this particular angle, that whatever angle we are considering, that wave is providing. Initially it started from 0, now it is starting from here. So there is an angle difference. So if I want to plot this one in the organ diagram or this phasor diagram, what we have to do, we have that x and y axis. Initially my wave was, if we just consider this was my first wave, so amplitude didn't change. So then next there is a change in the angle. So it changed the 45 degrees, right? But amplitude has no change in this one. Now if we just consider that okay, initial equation of any function, if we just consider that it will come a sin omega t, because there is no phase change. But here you can see there is a phase change and that is some angle, we can consider it is a 45 degree. Then you can write it that this is f of x equals to amplitude has no change, then it is coming sine, hold on a second, I will just remove this one, sine omega t plus 45. So because of this change. Okay. Now if we go further, what will happen? So let's take a look. Okay, the next one. So next one, if we just want to draw that, it will happen. So previous one, I'll draw the previous one here once, it will help us. So previous one is this one. Now this one, there is a, if you just consider that t equals to by 4, okay, time is changing, velocity is v, and in this particular case you can see the wave is moved so here you can see this much change here, and here you can see there is a complete half wave is shifted, right, almost. So there is a huge shift here, you can see. Now if you just try to plot this one again, if you just go to the previous page, you know that okay, where is the lambda by 4, you know, you will get the lambda by 4, then lambda by 2. Here also you can start that okay, there is a shift, this one will be your lambda by 2, right. Now you want to plot this one in your diagram. If you want to plot this one, again you have to draw a circle. Then previously this is your wave, it is located here, but in the current situation the wave is rotated again, there is an angle change, there is a phase difference here, phase difference between this particular wave, there is a phase difference between this wave. So if I just consider that this is the wave number 2 and this is the wave number 3, there is a phase difference between wave number 2 and 3, and there is a rotation. So now new will be coming like that. So now in this particular case you can say that there is a change in the phase, and we are representing this entire wave based on that angle change. That is called this is called the phasor diagram. The phase we are representing, the phasor diagram we are showing it here. So if that is changing from one direction to other direction, and it will go like this direction. In the next slide I will show you how they are going in the entire cycle based on this time change. So, when there is a time change, wave will propagate in one particular direction and there will be a phase change. Here also if you just consider the amplitude is same amplitude, we did not change the amplitude. Even if we just consider that same equation, that okay, this is the same amplitude, I am not changing the amplitude, this will be sine omega t plus 90 degree, that this is my phase difference. Okay. So, now we will just go to that. So, I will not go and draw each and all the diagram. Here if we come, you can see the similar kind of pattern here. So, what you can see here, you can, this one I already showed you using a when t equals to 0, t equals to 0, your and then there will be a no phase change, you can see it is in 0 position. Then when there is a change in the time, that okay, t equals to this, and you can see there is a 45 degree angle difference, right, and as well as in the wave also you can see there is a difference. The next one I already showed this one also, that if we just compare this particular wave, that is wave 1 and no, this is wave 2, this is our wave 1, this if we just compare wave 2 with wave 1, what we can see, that there is a wave propagates in this particular direction and there is a difference between this and this also. And that is we are reflecting here, that when t equals to this one, you can see in phasor diagram that okay, so vector is moved in particular direction and this angle will be something 90 degree. Now, if you go further, that when okay, t equals to your 3 t by 8, so you can see that again there is a change in this position of this wave and that is reflecting here in this particular angle. Not only that, if wave will move further, that okay, this is my wave 5, and if it will go further, if it is 6, you can see that there is a complete half wavelength is changed between the first wave. If we just consider wave 1 and wave 6, you can see they are completely in a opposite phase, this particular wave and this particular wave, and the wave propagates in this particular direction through the positive x direction. So, now if you just consider that wave 1, which is your 0 position. So, if you just consider your wave 1 and it is in the 0 position. Now, if you, this one is your wave 1 and now the wave 6, you can see there is a completely half lambda by 2 difference, you can see it here, and lambda by 2 difference means we already showed in that lambda by 2 means total difference will be in pi. So, that you can see it, that wave is completely moving in a opposite direction here, and that is representing in this particular diagram. So, that I am also showing it here, that okay, that this one is the wave 1 and this one is the wave 6, which is almost lambda by 2 wavelength difference, path length difference, and also this will be completely opposite direction of that. So, there will be a pi phase difference between these two waves. Now, if we go further, that okay, wave 7, wave 8, wave 9, wave 10, if we just come, you can see gradually again this wave propagates through this x direction, and then wave is starting from this one and following this path. In this particular case, time equals to 5 t by 8, and also there is a angle difference, and this is the angle. Now, if we keep going on in this way, you can see after a certain time in this particular case, that wave 10, you can see there is a completely one full wavelength difference between the first wave, but they are both are in a same phase, and that is the reason if you just look at this diagram where we are maintaining the phasor diagram, you can see that wave started rotating in this particular direction. We are getting in all the angle, and it finally rotate and came back to actual position. That I will just use a different color, that will be easier to understand. Then finally the wave back here. So now even in this diagram also you can see it, the both the waves are almost in same phase, but if you just consider that wavelength wise here completely one wavelength different than the first wave. So if you just consider that the wave 10 and wave 1, they are in same phase, amplitude is same, and but difference is that one full wavelength. Okay, this is the difference. This is the difference between these two one full wavelength. So I'll stop it here today, and then we'll discuss more about this, how when there is a phase difference, how we have to consider that wave, how they are interacting with each other. So you can think that okay, there is a wave is going, and then two wave will come and form an image. So why do we have to consider all of this? But this is very important, because in any kind of microscope or even electron microscope, we cannot consider that only one electron is coming and giving us an image. The multiple electrons are coming, they are interacting with the samples. Some are scattered electrons, some are unscattered electron, and they are converging. They are converging in a different way. Sometimes they converge in a such a way that will boost our signal, and some are converging in a such a way that they are damping the amplitude. So that we are going to discuss in the next class. Thank you all for your attention.